Hi everybody, Doc here. This is our Calc 1, Lesson 2, Section 1, 2, still Day 1. And today we're going to talk about mathematical models, a catalog of essential functions. Okay, so mathematical models. Is what today's going to be about. Okay, so we use mathematical models to make predictions on a lot of things. They describe real-world phenomena. Okay, so we have population growth when we estimate the speed of a falling object, or most recently, the coronavirus or other viruses, infectious diseases. Now, I put a video up on Sakai for all of you to watch on that. A lot of it you might not understand now, but hopefully by the end of the semester when you go, or by the end of the month, I should say, when you go back and take a look at it, there's going to be a lot more that you'll understand. So I also have this article that I'll be putting up on Sakai, the coronavirus outbreak mathematical model. I just thought it was kind of interesting to see, because we're always saying, where are we going to use it? Where are we going to use it? Where are we going to use it? And right now, we're using calculus a lot to make predictions and to help us make decisions because of this virus. Now, you're going to see equations here, but then you'll see something that has like a dv/dt. This means with respect to time. This is a rate of change, and this is what calculus is all about, rates. So you're going to see that often as we go through and take a look at this. This is an integral sign. I don't expect you guys to write any of this down or to know it. I just want you to take a look. Here's an integral sign, okay, which is integration, which we'll also be learning in the second or third week of class. So that's interesting too. And then here's the mathematical model, which has the, it takes a look at the comparison of the exact solution and the measured data of the total number of deaths, which come up here. So you can see how accurate that is. So that's pretty interesting. Here's another exponential growing of the total number of COVID-19 cases in Austria at the initial stage of the coronavirus. Okay, so this is the curve. And then I just want to point out quickly again, when you see, when I'm looking at this article, you can see this over dt over dt. Anytime you see that, that means it's a rate. And we're dealing with calculus, a rate of change, okay? And let's see if the last page has anything interesting on it. Nope, just all the bibliography. So anyway, I wanted to share that with you. And I will put it up on Sakai in case any of you want to take a look at it. All right, so today is going to be less of a math problem solving day and more of an informational day, just looking at different kinds of mathematical models. We have a linear model. Linear is just what it sounds like. So these are your lines. Linear models can be our equations, y equals mx plus b, or it might be empirical data. So data that you're putting up that ends up being in line, which ultimately can be represented by an equation. So let's take a look at some examples, and I'm going to refer to this book. taking a look at some of these examples. And again, we're just talking about linear models and how we can represent things to understand them better. This says, as dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at the height of 1 kilometer is 10 degrees Celsius, express the temperature T in Celsius as a function of the height, assuming that the linear model is appropriate. Draw a graph of the function. What does it represent? What is the temperature at the height of 2.5? Because we're assuming it's a linear function, we can write it. See this? Y equals mx plus b. But here it's t equals mh plus b. We're given that T is 20. Okay, we're given the ground temperature T is 20. And that's at D when the height is 0. So we can put 20 in here and 0 for the height. And we can simplify it. So we find out that our y-intercept is 20, which is our starting point, which we already knew. We're also given that T is 10 when the height is 1. So now we can put that into the equation. And when we do that, we can actually take this equation and solve for m just by bringing the 20 over, and then we get m equals negative 10. Negative 10 is our slope. So the required linear function would be t equals negative 10h plus b. So again, we first were able to find our y-intercept. We saw for b. And we used a point, another point, to plug in and solve for the slope. And once we had that, we could get our linear equation according to this problem. Now B says the graph is sketched in figure 3. And you can see it over here in figure 3. The graph is sketched. The slope is negative 10, as we already said. And this represents the rate of change. You're going to hear rate of change a lot. Anytime you hear rate of change, talking calculus. And the temperature with respect to height. And C, at the height of 2.5, what would the temperature be? So now we're going to put in 2.5 for the height, solve, and we see that the temperature would be negative 5 degrees Celsius. Now for the examples, again, if you have a question, of course, if we're together, you can just ask me in one of our Zoom call meetings. You can ask and answer in the comments section of the YouTube video. You can, and if you're in my class, you can send me a text or email also. So if you have any questions, just let me know. Example 2. All right, example 2. Here we have empirical data. So the first one was based on the line. Now this is empirical data. We have a table that lists the average carbon dioxide levels in the atmosphere in parts per million in the observatory in 1980 to 2008. We're going to use a table to find the model of the carbon dioxide levels. So here we have all the data. This is the hard data that was collected. And we go along the years and we just plot the points. Now that the data points appear to lie close to a straight line, it's natural to choose a linear model, but there are a lot of possible lines that could approximate these points. So which one should we use? So one possibility is the line that passes through the first and last data point. So you could take this point and this point and solve for a slope to get an estimate, and that would take you a line through here. You don't have to use those two. You could use, maybe you feel like this one and this one would be a better model, then you could use those. And that's just with researcher experience. But down here is what the line would look like if they took the first and the last. And again, they took the points and they put it into the slope formula. Y sub 2 minus Y sub 1. Remember the formula. Over X sub 2 minus X sub 1. That is your slope formula. And that's what allowed us to get now our equation. So we have our slope. And we have a point. Well, actually, we have lots of points. We take our point. Here, which one did they use? They used the first point, 338. Okay, so we're going to use that point in 1980. And then use your point slope formula. Let's review that. Y minus Y sub 1 equals m times the quantity x minus x sub 1. Okay, so we're using the point slope formula there. We simplify and we get our linear model. Okay, so that's how you would look at your linear models, either using an equation given to you or using empirical data points. Let's go on to example 3. Now, example 3 says we're going to use the linear model given by example 2 to estimate on average the carbon dioxide level for 1987 and predict the year 2015. That's what models are often used for, is predicting in the future. So we're going to take our model, which didn't look like they actually wrote down the model. So let's see. Let's write it down so it's a little easier to see here. All right. C equals 1.675 T minus 2977.8. Okay, so we want to use this model to predict okay, they're using the actual equation from up here because they did a second one. Okay, so let's take a look at the second one so you don't get confused when you go back. They did a second part. They picked two different points, this point and this point, and then they did another line, and then they used this equation. So we're going to use this equation here so that you don't get confused when you go back and take a look. So here's the second equation that they did. 6, 5, 4, 2, 9 T minus 2938.07. Okay, so again, just to reiterate that, they picked two different points just to compare the lines. This is the second part of example 2. They used two different points and they got a similar line but different. So they're using that for this example 3. So now we want to look at 2015. So we take a look at 2015. We're going to put our numbers in from our data points and to predict what we're going to have in 2000. Oh no, we're predicting 2015, and we're going to use the level for 1987 to predict it. Okay, so let's take a look. So 1987 here, and we're going to put our value in. We actually put the year in here. This was always kind of strange for me at first when I started calculus, but then, you know, when you realize that the year is just a number, and when we have it consecutively, it's just adding up year after year, then it makes sense. So we just put the actual year in here, and we see that we had 349. So if we go back up and we take a look at 1987 and we come up to the line, how good is our estimate? It's not too bad. Okay, so here's our estimate. How good is our estimate, 349? It's pretty good. So we're like, well, our model is not bad. So let's see what it could possibly be in 2015. So we come down to the same equation, and instead of putting 1987 in, we're going to put 2015. So here, I put that in, and I, again, just putting in the year, multiply these two, subtract, and we get approximately 395.32. Okay, so here's 2010. 2010 was up at about a little over 380. So we're saying if we continue this same, we would get 395.32, and that does make sense. Okay, so again, let me pull this down. Sorry, sometimes it's hard to remember I'm on the document cam. Here's the line. 2010, if I come up 380, if I continue this line, does it make sense that in 2015 I would be at 395.32? And it certainly does. So we did a good job estimating with our model. And that is if all the other situations remain the same. Okay, so there's example 3. Now, we're going to talk about the next kind, which is a polynomial model. Okay, polynomial model. Again, I'm going to stay here with the book because it has some really good pictures, and I told you before I'm not the best artist. So we have a polynomial model. You should recognize this. This is just from the definition of a polynomial. Okay. And when we're talking about a polynomial model, that means we could have a cubic equation, we could have a quadratic equation, we could have an equation such as this one right here. Okay, so these are polynomial model, and this is of the degree 6. The degree is always the highest exponent. The degree is the highest exponent in the equation. So here we have a 6-degree equation with a degree, or a 6-degree equation here for a polynomial model. Now, a polynomial of degree 1 would be a linear equation. Okay, we already went over that. Degree 2 would be quadratic. And let's take a look at some of those examples. Okay, well, here's a simple parabola that was just moved up and over. Right here's the equation. Here's a parabola that was flipped over by putting a negative in the front. We have some of our cubic equations here. Can look like this, can look like this, can look like this. You can do a lot of different things to your variables to cause different transformations. So if you take a look at example 4, quickly, and we see here that we have a ball drop from the upper observation deck of the CN Tower, 450 meters above the ground. And here's the height. 1 second intervals in the table 2. Find the model that fits the data. And the model that fits the data looks like this. Okay, quadratic function. All right, so moving on. Power functions. Power functions are functions that look in the form of, we'll take a look at some of the designs again, but power functions you have a base to a power. Okay, those are your power functions. Now, A might be n, just as a positive number. A might be 1 over n, which is the fraction, still positive. Or A might be -1. And again, we're going to say in this, n is positive. So let's take a look at what that would look like. Back to the book. And back and forth. Okay, here is what it looks like if n is positive. We have f of x equals x to the n. For n is 1, 2, 3, and 4, and 5. So this is our linear, quadratic, cubic, fourth power, fifth power. Notice how they alternate between looking like a parabola and looking like a cubic equation. The difference is this part here starts to get flatter and wider than this part as your exponent goes up. Same with your parabola. The bottom here, notice it gets flatter right here. Okay? So, again, they show you the general shape here. Here's a nice example of what I was just talking about. You have the parabola. The higher up your exponent goes, it will be even to remain a parabola. Here's squared, fourth, and sixth. You can see squared is your normal parabola. The fourth power. So now if we go back looking at this graph, you can see as we discussed, here's the regular parabola, y equals x squared. And you can see as my exponent increases, my parabola actually gets wider and flatter. So my y to the fourth is my red, and my y to the sixth even a little more. And that's what happens when it's an even value for your power. Now, if it's odd, it's going to look like a cubic. So this right here is x to the third. And then the even flatter one is x to the fifth. And that will continue as well. Now, if we want to take a look at when we have 1 over n, in other words, if it's a root, okay, so if it's a root function, then we have some different things to consider. If it's a root function, which is actually x to the 1 over n, x to the 1 over n is the same thing as the nth root of x, okay? And when we're talking about a is 1 over n, that means we have root functions. If the root is even, we cannot have a real number underneath an even radical. That will give us an imaginary number. So that means that anything that is below 0 on the y-axis will not enter into the domain. It has to be 0 and above, 0 and positive. So that's why if the root function is even, you'll have it look like this. However, if the root function is odd, this is your cube root of x, then it can go underneath the x-axis. In other words, the cube root of -8 is -2. Because -2 times -2 times -2 is -8. Okay? So those are your root functions. What happens when it becomes a reciprocal function, in other words, if a equals 1, so now we have a reciprocal function. If a is -1 and now we have 1 over x, if a is -1 and now we have 1 over x, I hope you can see that it's a little small. Okay, we have 1 over x. Then we have this hyperbola that develops. And you can see in the hyperbola here is the first quadrant. So depending on whether n is positive, whether it's 1 over n, or whether you have the reciprocal function, will depend on what your power function looks like. Now the next one would be your rational functions. Now rational functions look like fractions. Imagine that, because they're rational numbers. Okay, so we have a polynomial on the top, polynomial on the bottom. And here's an example of a rational function. Now here I have a polynomial 2x to the 4th minus x squared plus 1 on the top, x squared minus 4 on the bottom. If I look at them separately, their domains are from negative infinity to positive infinity because they're polynomials. But as soon as I put one of them on the bottom of the fraction, now I have to take a look at my domain, because I cannot have 0 on the bottom of a fraction. So I need to factor the bottom and take a look at where those are zeros. And I can see that I cannot put in a 2 or a negative 2 into the bottom. So that would mean that my domain would be for all x such that x cannot equal positive or negative 2. For all x such that x cannot equal positive or negative 2. Now, it often happens that we have functions that are added together, divided, multiplied. When that happens and you have more than one type, we just simply call it an algebraic function. So some of the algebraic functions, as you can see here, I have this function, it's rational. I have a root down here. I have a root over here. This all together would be an algebraic function. If I take a look at some of the sketches of algebraic functions, they can often take form of many different things. So here we have this one, x to the 2/3 times x minus 2 to the 2nd. This is crazy. Comes down, comes up, and goes back over. Okay. Now, moving on to trigonometric functions. The trig functions, we have our sine and our cosine, which are our base of trigonometry. If we look at sine and cosine without doing any kind of transformations to them, we know that our range for sine and cosine would be -1 to 1. Because on my y's, that's all the higher it gets. Again, this is without any kind of transformation. Same with the cosine model. Other things to note about the sine and cosine models is that they're periodic, which means they follow a pattern. If we take a look at our sine function, we have our 0 at 0 for sine. We also have it at pi, 180. We have it again at 360. And that pattern continues. So we will say sine is equal to 0 whenever I have 180 times any integer, whether it be positive or negative. Integer. So we're talking -2, -1, 0, 1, 2. Okay, those are integers. So that's when we get our zeros. The other thing that we need to look at about the sine and cosine function, they are periodic in a period of 2 pi by themselves. Again, this is without changing them anyway by multiplying, stretching, taking half, whatever. But in itself, after 2 pi, it repeats. So if I start here and I travel 2 pi, I'm going to start all over again. Same with my cosine. Start here, travel to 2 pi, then start all over again. So that's when we say that they are periodic functions, okay, for all values of x. Now our exponential functions. exponential functions are a little bit different than our power functions in that our power functions have a base variable. Okay, we're going to take a look at this again. Our power functions, okay, x to the a, and then our exponential functions mean that my base itself is going to be the constant. So my base is the constant. So that's the difference between power functions and exponential functions. Now you can have positive or negative here. If you have a positive a is going to be greater than 1. For instance, you have a positive, maybe population growth. Or if a is less than 1, you're looking at a population decay. Okay, so here we go, looking at some exponential functions here. Here I have the most common, which is y equals 2 to the x. Base 2 to the x. And then if I take the reciprocal of that, which is 1/2, you see it just flips around the y-axis. Now the logarithmic function, which is also an exponential function, an inverse of the exponential function, instead of going through the y-axis at 1, we're going to travel through the x-axis at 1. And you can see they look quite similar, but again, they're inverses of each other. Now, similar to when we looked at the parabola and also the cubic equations, or the even and odd exponents, you can see here, the bigger my base, the more compact it is. When I start getting a smaller base, it opens up a little more. And the green up here is log 2, base 2 of x. Okay? All right, now, the next part just wants to see, have you been paying attention? What kind of functions are these? Now, I wrote this a little bit bigger because it was hard to see. 5 to the x, well, that's our exponential function. It has a constant at the base. B says x to the 5. That's our power function. It has our variable as the base. C has a lot going on. It has a rational here, and then it also has a radical, so I would call that an algebraic function. And then finally over here, D, 1 minus t plus 5t to the 4th. This is just your average polynomial with a degree of 4, since 4 is the highest exponent. Okay? All right, so if you have any questions on this section, feel free to message me, send me an email. If you're watching this on YouTube, you can put a comment in the comment section. And that's all for today. And then we're going to start up here on Section 1-3, still at day 1. All right, take care. Peace.